Hello, in this video we're going to see the second principle of mathematical induction. So this is similar to the first principle of mathematical induction, where we have to check for the smallest n, in this case like n greater than or equal to 1, we have to check for n equal to 1, and you assume it's true for n, and you're going to try to check if it is true for n plus 1. So I wrote down here those 3 steps. So let's see. If we need to prove that n squared is greater than n plus 1 for all n greater than 2 using the second principle of mathematical induction, so I'm going to check for the base n, which is for n equal to 2. So here we have 2 squared. Is it greater than 2 plus 1? Well, 4 is greater than 3, so it's correct, it's true. Then you assume that for all n greater or equal to 2, n squared is greater than n plus 1. And I'm going to try to prove that for all n greater than 2, n plus 1 quantity squared is greater than n plus 2. Why n plus 2? Because you replace every n with n plus 1, which is the next term. So what we have here is that n plus 1 quantity squared must be greater than n plus 2. This is our goal. So here on scratch paper we're gonna write down the goal, that n plus 1 quantity squared is greater than n plus 2 for all n greater or equal to 2. This is where we need to get into. So n plus 1 quantity squared is equivalent to stating n squared plus 2n plus 1 greater than n plus 2. So we stop here and think. We know from the assumption n squared is greater than n plus 1. So what we could do, if I add from the assumption, if I add 2n plus 1 to both sides, 2n plus 1. So I add this. So we add in 2n plus 1 to both sides of the assumption. What we're going to end up with is n plus 1 quantity squared greater than 3n plus 2. But here is the goal. The goal is to prove that n plus 1 quantity squared is greater than n plus 2. But I end up with n plus 1 quantity squared from the assumption is greater than 3n plus 2. Well, we know that 3n plus 2 is greater than n plus 2, right? Because 3n is greater than n, basically. The reason why, because it's 3n greater than n. Or even because 3 is greater than 1. And then we could use this argument. Even start with the 3 greater than 1. I would like to say, since 3 greater than 1, which is equivalent to stating 3n greater than n, multiply both n is greater than or equal to 2, which is equivalent to stating that 3n plus 2 is greater than n plus 2. This is all logical. I add 2 to both sides. So I'm cheating. This is what this scratch paper kind of helped me. Not cheating, but I'm going backward with this equivalent relationship. Because to get to this goal here, we will by something logical. So this is what we have. And then I'm going to say from the assumption, where we have n squared is greater than n plus 1. So if I add 2n plus 1 to both sides, we end up with n plus 1 quantity squared greater than 3n plus 1. Well, since 3n plus 1, let's call it here, from 1, 3n plus 2. So we end up with n plus 1 quantity squared is greater than 3n plus 2. But since 3n plus 2 is greater than n plus 2, from here, then n plus 1 quantity squared must be greater than n plus 2. End up at our goal here for all n greater than or equal to 2. So this is basically right here is the proof. This helps me achieve what I need to find. And the conclusion is, for all n greater or equal to 2, n squared is greater than n plus 1. Let's see this example here. We need to prove that n factorial greater than n squared for all n greater than or equal to 4. So the first thing you do is you check if it is true for n equal 4, and as we see, is 4 factorial greater than 4 square? 4 factorial is 1 times 2 times 3 times 4, and 4 square is 16. This is equivalent to stating that 24 is greater than 16, so we're good. Second, we're going to assume that for all n greater than or equal to 4, n factorial is greater than n squared. So third thing, we need to prove that for all n greater or equal to 4, that n plus 1 factorial is greater than n plus 1 quantity squared. So all what we need to do is that, so here on scratch paper, we start with the goal. This is where we need to reach. So this is equivalent to, if you think of factorial, meaning 1 times 2 times all the way to n plus 1. So you don't stop at n, you stop at n plus 1. So what I need to prove is that if I multiply all these numbers, is this greater than n plus 1 quantity square? So 1 times 2 times 3 all the way to n, this is like n factorial. So n factorial times n plus 1 greater than n plus 1 quantity square. Still, this is what we need to get into. If I stop for a moment and I see what I have for the assumption, what do I have is n factorial greater than n square. So I know that from the assumption, n factorial is greater than n squared because that's my assumption. So if I multiply both sides with n plus 1, I get this. So now this is what I need to get into based on what we have. So if I just can say that n squared times n plus 1 is greater than n plus 1 quantity square. So let's see what we have here. This is n factorial times n plus 1 greater than n basically to the third plus n squared. So now the question is n to the third plus n squared greater than n plus 1 quantity square? Meaning, is n to the third plus n squared greater than n squared plus 2n plus 1? If I subtract n squared to both sides, we get n to the third is greater than 2n plus 1. That we know for all n greater than or equal to 4, because n to the third is greater than 2n plus 1. You could use another proof by induction as well to prove it, but we know it's true. So I'm going to say since n to the third is greater than 2n plus 1 for all n greater or equal to 4, see, now I go backward. I go backward this way. Then this is equivalent to saying n to the third plus n squared is greater than n squared plus 2n plus 1, which is equivalent to saying that n to the third plus n squared is greater than n plus 1 quantity square for all n greater or equal to 4. Now, from the assumption n factorial greater than n squared, well, n factorial if I multiply by n plus 1 because it's a positive number, nothing changed, just multiply by n plus 1 for all n greater or equal to 4. This is equivalent. From the assumption we could get here. If I call this one inequality 1 and this is the inequality 2, so n squared times n plus 1 is the same as n to the third plus n squared. So what we could get is n factorial times n plus 1 is greater than n squared times n plus 1, which is also greater than n plus 1 quantity square. Let me stop here for a minute, just on the side. So this is the same as saying for 1, if I would say 7 is greater than 6. And then for number 2 is the same as saying 9 is greater than 7. So from 1 and 2, I would say you have 9 greater than 7 and 7 is greater than 6. So 9 is greater than 6. So that's what exactly I did here. 9 is greater than 6. That's what I used, the same logic. So now I would say that n factorial n plus 1 is greater than n plus 1 quantity square, which is our goal for all n greater or equal to 4. Now we're done. We could say therefore n factorial is greater than n squared for all n greater than or equal to 4. So this example, we need to prove that 1 plus 2 plus all the way to n is less than n squared. So we're gonna try to write the 3 assumptions. So let's write the 3 steps. So here we are. We check for n equal to 2 because this is for n greater than 1, or we could say n greater than or equal to 2. So for n equal to 2, so what we have is 2 less than 2 squared. So 2 is less than 4, so yes, it's true. And then we're going to assume for all n greater than 1 that 1 plus 2 plus all the way to n is less than n squared. And the third thing is to prove for all n greater than 1, and 1 plus 2 plus 3 all the way to n plus 1 is less than n plus 1 quantity square. So right here, what I'm going to try, assumption. So from the assumption, this is what we have, 1 plus 2 plus all the way to n less than n squared. So as we see, this is the goal right here. So if I add n plus 1 here, and I add n plus 1 here, I will end up with the following: 1 plus 2 plus all the way to n plus n plus 1 is less than n squared plus n plus 1. So I'm almost done with the left hand side is done, but all what I need is to prove that n squared plus 1 plus n is less than n plus 1 quantity square. So n squared plus n plus 1, is it really less than n plus 1 quantity square? So we know that n squared plus n plus 1 is less than n squared plus 2n plus 1, right? So as we could see, if we subtract n squared, so we're going to end up with n is less than 2n, which is true. N is less than 2n, right? Or even you could say that 1 is less than 2 if I divide by n both sides. So from here I would start. I would say since 1 is less than 2, which is equivalent to n less than 2n, which is equivalent to saying that n squared plus n plus 1 is less than n squared plus 2n plus 1, which is equivalent to n squared plus n plus 1 is less than n plus 1 quantity square. And we stop here. Then you go to the assumption for all n greater than 1, 1 plus 2 plus all the way to n is less than n squared. So by adding n plus 1 to both sides to the assumption, this is the left hand side for our goal. So what we are gonna end up with is that equivalent to saying 1 plus 2 plus all the way to n plus 1 is less than, and we could say that from 1 and 2, this is common here, right? So I would say from statement 1 and 2, 1 plus 2 plus all the way to n plus 1 gonna be less than n plus 1 quantity square, and this is the goal for all n greater or equal to 2, or which is our goal for all n greater than 1. And therefore 1 plus 2 plus all the way to n is less than n squared for all n greater than 1. I hope this is helpful.